Okay, so for this video we're going to look at impact problems, and we're going to look at calculating the displacement of this beam after the impact, and we're also going to look at calculating the force on the beam from the impact, right? So when dealing with impact problems, we basically use the conservation of energy to actually calculate everything, right? So we say that the change in kinetic energy plus the change in potential energy must equal 0 for the problem, right? So we can look at state 1. What I like to do is draw the two states together, right? So I have state 1 where this car or whatever is moving at some velocity v, right, and it has some mass, so we know that it has some kinetic energy, right? And at state 1 nothing is happening to the beam, so it's basically just fixed, it's stationary. So this has no energy. Its energy is equal to 0, and then the car has some kinetic energy. Cool. Then at state 2 we expect the beam to deflect some amount after the impact, and let's say that's the front of the car, right? And the car is going to come to rest. So the energy from the car is equal to 0 at state 2, and the energy from the car at state 1 is equal to some value, right? But for the beam, its potential energy, because the beam is going to be storing potential energy, it's going to convert all of this kinetic energy into potential energy as it deflects, right? So its potential energy at state 1 is 0, but its potential energy at state 2 is equal to some value, right? And we can basically do, I guess, an energy balance, right? So we'll look at the change in kinetic energy plus the change in potential energy, and we know all of that must equal to 0. So the change in kinetic energy is going to be given by, we can do it for state 1, so it's going to be state 2 minus state 1. So KE2 minus KE1, which is going to be equal to 0 for state 2 because it's at rest, and then minus a half mv squared, right? So the change in kinetic energy is equal to minus a half mv squared, and we expect it to be negative because going from state 1 to state 2 it loses kinetic energy. If we regard this as our entire system, it loses kinetic energy and it gains potential energy. Yeah, I hope that kind of makes sense. And then we can look at the change in potential energy, right, which is then going to be PE2 minus PE1 equal to 0. Sorry, no, that's going to be equal to the potential energy at state 2. If we regard the beam as a spring, right, we can say it's equal to a half K equivalent, right, times delta squared. Okay, so that's at state 2, and at state 1 it's 0. Cool. So then if we substitute both of these into our equation, let me just erase those. If we substitute both of these into our equation, so over here we get delta P is equal to a half K equivalent delta squared if we substitute that back into this equation over here, we get minus a half mv squared plus a half k equivalent delta squared equal to 0. So then we get a half k equivalent delta squared is equal to a half mv squared, right? The only thing we need to determine then is our k equivalent. So I got these equations from the MVR formula sheet. I don't know where these equations are in Shigley. Yeah, so if we have a cantilevered beam, right? So basically, which is what we have over here, right? So if you have something like this and your load is applied at the end, then this is going to be your K equivalent. That's going to be the equivalent stiffness for the beam for this problem. And then if you have a simply supported beam with the center load, so you have something like that with the load at the center, this will be your K equivalent. And then if you have a fixed beam, so something like this where it's fixed at both ends and the load is in the middle, then this will be your K equivalent. So a K equivalent for this problem is going to be this value here. So we're going to get a half 3 EI over L cubed times delta squared is equal to a half mv squared. Okay, and from the problem you have all of these properties, and then you can solve for the deflection. And then from this, if we wanted to then calculate the force, since we modeled it as a spring, we know that the force is equal to kx, right, which is equal to k equivalent times delta. So once you've solved for delta, you can then solve for the force by saying delta is equal to F divided by K equivalent. What? No, we're solving for the force. So the force will be equal to K equivalent times delta, which will be, what's this? 3 EI over L cubed times delta. Cool, I hope that makes sense.